Greetings. So in the previous episode we just stated something that the good model should be a minimal one for defining the semantics of logic programs, but minimal. So what should it mean? That's what this video is about. So we will be dealing through the whole semester with so-called posets. POSET. That is shortened for partially ordered sets. Partially ordered sets. Now, it's basically just a set with some relation, a binary relation, which is just less than or equal to sign, denoted by this sign, but it's not necessarily the actual relation which you might know from, say, between the natural numbers or the real numbers and so on. That can denote that thing, but can denote many other things. So the poset, and the sad news is the posets are usually also denoted by P, by capital P. So poset is a tuple, it's a pair, P, and as the neck or where P is just a set of objects, of elements. Well, in practice we will order the truth values themselves, 0 and 1. 1 will be the greater amongst them, of course, and the assignments will be ordered pointwise, and two variable assignments might or might not be comparable according to this relation, because this guy here is a relation. So this less than or equal to is a relation, a binary relation over P, over the set. You can also say that this means that this guy is a subset of P times P, if you are familiar with this notion. So it's just something is either smaller than or equal to another thing or not. But this smaller than or equal to should satisfy some laws, so such that so first, for each element of P, say X, we should have X being comparable with X. Yeah, that's fine. Okay, so it's basically the numbers usually do that. So let's move to the second one. So if I have 3 elements, now if X is lower bound of Y and Y is lower bound of Z, then X should be lower bound for Z. Now there are names for these properties. So this guy here is called reflexivity, and that guy is called transitivity. So the relation is reflexive and the relation is transitive. And there is another one, a third one, which says that if I have 2 elements and X is lower bound of Y and also Y is lower bound of X, then they have to be the same. Yeah, that's the third one. So this is basically what is called antisymmetry. Or the relation is antisymmetric. And if I have an arbitrary set of objects and an arbitrary relation which satisfies these axioms, then these guys together form a partially ordered set, a poset, and this guy here, the relation itself, is in that case a partial order. Now let's see some examples. Yeah. So, examples. Of course, we can have the natural numbers, say 0, 1, 2, and so on, and the standard ordering. That's fine. So let's just check these axioms. Every number is smaller than or equal to itself. Okay. If x is a number and y is a larger number and z is an even larger number, then well, z is larger than x. That's fine. And also if they are, so if I have two numbers and one of them is a lower bound of the other and the other one is a lower bound of the former one, then they have to be the same. So this is a total relation. Yeah. So that's fine. And actually, you can just work with the integers, with the rationals, or with the real numbers, also with the standard ordering of them. That's also fine. Now, this is some very special thing, because in these partial order sets we actually have a total order, so they are totally ordered. What does it mean? It means that for each x and y, we either have x being a lower bound of y, or y being a lower bound of x. So no matter how I pick two elements, they are always comparable. Now this is not always the case, because you might be familiar with the following notion. So when x is a set, that's also an example, or when x is a set, then px as the power set. It is a set of all the subsets of x, and the subset relation, like this, is also a poset. Basically, because if say y is a subset of x, yeah, so it's an element of px, then of course y is a subset of itself, yeah, of course. And if y1 is a subset of y2 and y2 is a subset of y3, then of course y1 is a subset of y3, so transitivity is also fine. And the third one was if y1 is a subset of y2 and y2 is a subset of y1, then of course they are the same. So yes, power sets are always partially ordered sets, but not always totally ordered sets. So let's just see it a bit more in a bit more detail. So if x is just say pqr, then px, how do I get this px? So this is what's called a Hasse diagram. It's a so-called Hasse diagram. We are just depicting all the elements of the partial ordered set. So this guy is the topmost, because if one element is lower in the diagram than another one, so it's connected by a continuous path leading upwards to the other element, then and only then should they be related by the less than and or equal to relation. So in this case, for example, I'm writing here the PQ, and because from PQ I can move to PQR by moving always upwards, and this is why it's depicting that PQ is smaller than or equal to PQR. And of course, PR is also smaller than PQR. This is a subset of it. So Px is equipped with the subset relation here, and also QR is a lower bound for PQR. But these three elements are not related at all. So neither PQ is a subset of PR, nor PR is a subset of PQ. So this is not a totally ordered set. It's just a partial ordered set. And of course it has some more elements. So for example, this P here, this guy is a subset of PQ and it's a subset of PR as well. We also have this R here, which is a subset of PR and QR, but it's not a subset of PQ. That's why I'm not drawing a line. But this part of the diagram depicts this R is smaller than equal to QR because there is a path leading there. It's a subset of PR because there is a path leading there. It's a subset of PQR as well because there is a two-step path leading upwards. And of course, there is a third guy here, the Q. Yeah, and also the empty set is always a subset of any set. So that's the final element of this 8-element poset. So this is just another partially ordered set, but it's not totally ordered. Now there is another notion, another set, another poset we can get. We can get from X. Another example, probably it's better if I use another color as well. So it's X with button. So it's a so-called pointed poset. Pointed poset. This is just getting a new element, which is usually denoted by button, and placing this guy below all the other elements of X, and the elements of X themselves won't be related. So it says that it's just X plus the union of X and the button operator, and button being smaller than or equal to X for all elements of X. And of course it's also smaller than or equal to itself. So for example, this poset, when again X equals PQR, then X button is just the button and P and Q and R here and there and there. Yeah, so it's a 4-element poset in that case. Now this sort of poset will be used for the case of functional programs. The button will denote something like an infinite loop, an infinite termination, non-terminating computation, while P, Q, and R will denote actual values which our functions will be evaluated. And I will use this notion there, and this other one, this guy here, will be used for the semantics of logic programs. We will put those variables into a set which are true, and those guys which are left out are not put in the set. So that's how it's minimal, because a minimal assignment, this guy here is minimal because if you just think of it, then it means that nothing is set to 1, nothing is set to true, and all the variables are set to false, and that's smaller because maybe our last example. We still have 2 of them. Another example is the poset 2. Of course, we will use this poset 2 with the so usually we don't spell out explicitly the smaller than or equal to relation. So the poset 2 is just having 2 elements, 0 and 1, and 1 is larger than 0. Okay, so this will be of course used in the context of logic programs, so these will be the truth values initially. Later on we will have many varied logics. We will will have 3 values and 4 possible values in our logic semantics, but in the beginning we will only use the 0, which is for false, and the 1, which is for true. Okay, and also if another example, I'm just switching colors again and again. So also if say P is a poset and I is just some index set. Here index set means that it's just a set whose values will be used for indexing something, but it can be infinite. So that's what, so we will want usually index variables, say p1, p2, p3 and so on, pn, because usually we will need an infinite number of indexes, and even then we will need sometimes an awfully large amount of indexes. So 1, 2, 3 and all, it's just countable, so it wouldn't be enough for all possible scenarios. So, and I is an index set then p to the I. This is how it's called. So I have a poset and the set. I can write something which resembles to an exponentation, poset being the base of the exponential, and the set, the index set, playing as the exponent. Pi is the set of all the functions say u from I to p. Okay, we will see an example soon, equipped with the so-called pointwise ordering. The so-called pointwise ordering, which means that if I have a function, say u, and I have another function v, I will say that u is smaller than or equal to v if and only if it's smaller than or equal to v on any possible input. So for each possible I, for each input of the function, the u of I is the lower bound of the v of I. Yes, you see, this is okay, so it's a function argument, but you can view it as an index as well, so you can write like this if you wish, as a subscript, but as a subscript if you wish, and that's so that's why it's also called an index set, because some people prefer to use this notation for denoting the functions. This is the same, but in this course we will use this form more or less explicitly, so when we are talking about these posets. Now again, this is a bit abstract, so let's see another example. So for example, we have, if I have the set z of variables p, q and r, so I have these 3 variables, and is the set, is the index set, and 2 is the poset. So these guys have only 2 elements, so 2 is just 0 and 1. Okay, then 2 to the z is what? We have functions which map to each z, p, q, r, will get a value. So these are basically assignments, variable assignments. So it's just z to q, z2 functions. So for example, in this case, I can write a vector for such a function. So basically, So, for example, if I denote 0, 1, 1 denotes the function which just maps 0 to p, 1 to q, and r to 1. So the first place is for p, the second place is for q, and the third place is for r. Like then 0, 1, 1 is just this mapping, and of course 1, 0, 1 is the mapping when p is 1, q is 0, and r is 1, right? And so on. So these functions can be seen, can be viewed as vectors. These vectors might be infinite if you have an infinite number of variables, but that's not a problem for us. I will call them vectors even if they are infinite. So I think it's a bit easier to see when a function is essentially just like a vector. Now, okay, so these are the members of the poset, but let's just see the ordering itself. So two functions are related if they are related on all the coordinates in the very same direction. So for example, these two assignments are not comparable because on the first coordinate we have a relation like this, and on the second coordinate we have a relation like this, and on the third coordinate we have equals, which is fine, but in order to be comparable it has to be the case that all the elements are ordered in the same direction. So for example, 0, 1, 0 is smaller than or equal to, say, 1, 1, 0, because here in the first coordinate we have smaller than or equal to, and on the second and on the third one as well, or 1, 1, 1, like. And if you just think a bit about this possible shape of this of the diagram of this poset, you will get that we can just write the 1, 1, 1 as topmost element, because of course it will be larger, or at least as large on each coordinate as any other guys. And then say 1, 1, 0 is just below this guy, and the 1, say 0, 1 is below that guy, and 0, 1, 1 is below, but these are not comparable to each other because exactly for the same reason what I just showed you. For example, for the first two, like this, we have here 1 is larger than 0, so and 0 is larger than 1, so they are just point onto each other, so it's not less than or equal to, and neither the other way around. So these three guys are not related, otherwise not related. And also I have this 1, 0, 0 here, and I have this 0, 0, 1 here, and I have this 0, 1, 0 here, and they are related like this, and 0, 0, 0 here. Now this guy should be familiar, right? So what I see here, this is a poset which is pretty much the same as this one here. So again we have these 8 elements, and this lattice has the very same shape, and of course they are actually isomorphic, which means that I can just rename the objects, and the shape of this lattice will be the same, roughly speaking. So for example, if I have a function, then I can just map it to a set, say x in x, which are for which ux is 1, then, or z if you just used this set of variables. So in that case those will be included in the set which have a value of 1, so this guy here will be the PQR, this guy there will be the PQ, and so on. And of course the relations are preserved. So if in the original poset there was a relation between two elements, then and only then will be there a relation between the image of these two elements. Now it's fine. So it says that basically for any set Px equipped with the subset relation is basically the same as 2 to the x equipped with the pointwise ordering. This is the same, or we can use this sign denoting they are isomorphic. So basically they are the same up to renaming of the objects themselves. And usually we will prefer this bottom one, this guy, because later on we will introduce 3-varied logic and 4-varied logic, stuff like that. And it's much easier to handle things like 3 to the x or 4 to the x instead of the subset, so extending the subset relation itself somehow. So this is the notion with which we will go, the 2 to the x notion. So assignment are 2 to the x because we are not only using 2-varied logic during this course. Now, what should I tell you more about these partial orders? So right now we know that a model is just a variable assignment, so it's just a member of the poset 2-3 set. We have the large poset, all the assignments, and some of them is a model of the program, some of them is not a model of the program. Now amongst these guys, the models, I should choose a minimal one. That's what the semantic says. So, and what's this? What is minimal? So if P is a poset, so if I don't spell out the relation smaller than or equal to, then the relation is smaller than or equal to. So the sign is the default if I'm not spelling it out explicitly. So if P is a poset and X is a subset of CP, then say it's then an element X of X is, so it's a so-called minimal element of X if there are no elements below X within the subset X. So it's a minimal element of X if so if there is no element within X strictly below this X, which is the same as I'm saying for each Y element of the set X, we have Y being smaller than or equal to X only if Y is the same as X. Now this is the same, but it doesn't use an explicit negation, which is fine. So basically it says that no elements within X lie below X. And another related notion is a least element. That's different. A least element of X. Now being a least element means that every other guy within X is larger than this element, so they are comparable and in that direction. So if for each element of X we have that X is smaller than or equal than to pi. Yeah. So basically this means that all elements say all other elements of X are larger. Okay, so that's what it seems. Let's see again some more examples, because examples are always fine. So if I have this PQR, PQ, you know, the usual stuff, QR, PR, P, Q, R, and nada. So we have this, and I can pick, say, this as X. So this war stuff is P, is the poset P, and I have this X. Then P, oops, let's use yellow, then P, Q, and R. Since within X there are no element below P, this means that P is a minimal element. And also Q is a minimal element as well, because within X, because there is no other element within X which is strictly below Q. So these three elements are actually, each of them, they are minimal elements of X. Of course, if you pick a different set, then that set will have a different set of minimal elements. But you can see there can be more of the minimal elements. Now, the other four are not minimal because, for example, for PQ you can find P, which is strictly smaller and still within X. But here in this set there is no least element, because for a least element it should fulfill the property of being strictly smaller than all the others, or being smaller than or equal to all the elements of X. And there is no element which can satisfy this constraint, because, for example, for P, Q is not larger than P, so it's counterexample. Now for Q, well, P is not larger than Q. For R, well, Q is not larger than R. And for all the other guys, of course, the minimal elements cannot be larger than them, so there is no least element of X. And you have several minimal elements. Now, okay, so it can happen, but of course, if there is a least element, then it's unique. So if there is a least element, then it's unique, and it's a minimal element as well. So it's just a proposition. So if X has a least element, then it's unique. And of course it's also minimal. Now that's the statement, and in this subject we will prove our statements, almost all of them. So it's unique. What does it mean it's unique? It means that if X and Y are both least elements, of X, then X equals Y, so they are the same element. So there cannot be two different least elements unique. These are synonyms. So this is what we should prove. So let's say X and Y are both least elements. So then X is smaller than Y because X is least of X, and Y is a member of X. The least element means that this is smaller than each element of the set. So X, since this is the least element and Y is a member, then we have this. And also we have this, because Y is a least element and X is a member of X. And from these two and the symmetry, we get x equals y. Yes. And also, so it's unique and minimal. So for the and minimal part, so let's for the definition of minimality, so let's y be smaller than x. Y still being an element of x. Then x is smaller than y because y is a member of x and x is and x is least. And again, from these two, we immediately get that x equals y. So that's fine. If we have a least element, then it's unique. Now, what does it mean? It means that if there is a least model of a logic program, then it should be the one and only semantics, because it says that if there are many models of a logic program, so for example, in the previous slide, whatever, so in the previous example here, we can say that these x is a models of a formula, say P or Q or R, right? So this guy here is the assignment which assigns P force, Q force, and R force, and that's not a model of this formula, because under this variable assignment you will get force 0. But all the other members of this x set at least when variable to 1 to true, so this function will be evaluated to 1. So this is so each of these 7 assignments are models of this formula here. Now this is not a logic program because it's not a conjunction implication variable, sort of, but if you want to assign the semantics to such a set of models, then you should pick a minimal one. But amongst these 3, you do not have any really clue which is the better one. Well, at least at this point, you don't have a clue which one you should choose. But here there is no least element. And for example, if it would happen that there is a least element, like if these 4 elements, so those guys containing Q would be the set X of models, then of course there would be one and only one minimal element of the set, and in that case it would be absolutely a unique choice, so you can choose only that element if you have only one minimal element. Yeah. Okay, so if we have a least element, then it's unique, which is great. Now we are not only talking about minimal elements and the least elements, but there is a dual notion of maximal elements and greatest elements. So let's just modify these guys. So a maximal element of x means that if x is smaller than y, then they are the same. But this is again the same. No elements within x lie above x. Right? So it's just the same thing, just upside down, rotated. So a maximal element is an element which has no strict upper bound within the set, and the greatest element, that's the other thing, the greatest element is of x is if everything other is just below x. Yeah, so all other elements of x are smaller. Yeah, so of course these are almost the same, so they are just dual notions. And there is also a very related thing. So right now we know that, okay, so amongst the set of, so we should just, if we have a logic program, we should just compute somehow the set of possible models and pick a minimal element of these models according to this pointwise ordering of variable assignments. And if it happens to be a least element amongst them, then that will be the unique semantics. And we will see that this is exactly the situation which will happen. Now, speaking of these small and minimal and minimal and least elements, so if there is something which is resembling to the limit of sequences or limit of sets from analysis, from real analysis, from calculus. So it's just a slight resemblance, but it just looks like the limit superior. So it's if P is a poset, and X is a set of P, and say Y. Now, in the previous definitions, the least element of X and the minimal element of X are actual elements of X. Now, the so-called supremum of X and an upper bound of X is not necessarily a member of X, it's just, it can be another element of the poset. And if Y is in P, then Y is, so the first notion is an upper bound of X, so it's an upper bound of X. Well, we denote this, denoted X is smaller than or equal to Y. I usually won't rotate this sign, so it will always this less than or equal to, and I will just swap the two sides if I want to write this in the other way around. So it's X, the set X being smaller than Y, if all the elements of the set are smaller than or equal to Y. So if all the elements of the set are smaller than or equal to Y, and the supremum of X, and it also has a notion denoted, the supremum, the supremum of X being Y if Y is a lower bound, is an upper bound of X, and this is the least upper bound. So if Y is the, I can say the because right now we already know that if something has a least element, then the least element is unique. So if Y is the least element of the upper bounds of X, so I could say that is the least upper bound. Least upper bound of X. Okay, again, let's see some examples. So for example, if I have the pointed poset, so PQR, say, this is P, and I'm just picking a subset of the members of P, like this. So here we have no upper bounds, absolutely. Because an element is an upper bound of this X if the element is above Q and above or equal to R, but there is no common ancestor of these two guys. So there is no upper bound of X. If I would pick this guy here as X, then P is an upper bound. Because P is at least as large as P, of course, and P is at least as large as this button, the least element. Yeah. So P is an upper bound of this X. And of course, since there is only one upper bound, then this is the supremum of X. That's also P. And here in the brown case, there is absolutely no supremum, of course, because if your set is empty, then it cannot have a least element as well, because the least element is also a member of a set. So if the set of upper bounds is empty, then there is no least upper bound, so no supremum. But there is also a dual notion here as well. I think you are not surprised at that. So it's a lower bound denoted by y being smaller than or equal to x if for each member of x we have the other way around. So lower bound means just below all the elements of x or equal to. And the supremum, instead of the supremum we have the infimum. I'm almost sure that you heard this term in the setting of analysis, of real analysis. And the infimum is denoted by the wedge of x is y, if this is the greatest lower bound of x. So it's again, it's just the dual notion. Now let's just flip it back. Now for this x, for the brown part, we have that bottom is a lower bound because it's below both q and r. And bottom isn't the only lower bound, so bottom is the infimum of x in this case. Now in the other case, the infimum of that x, of the red x, is also the bottom. And bottom is the only lower bound as well. So in this case we have two different sets having the very same infimum and totally different supremum, because one of these doesn't even have any upper bound, of course. Okay, so that's the difference between infimum and supremum and stuff like that. Now we will use this supremum operator quite often, so it's instructive to get some grasp on the notion. So what does it mean? And what should I tell you right now? I'm just checking the notes. Yep, exactly. This is unique and some supremo facts. We will use this supremo operator, we will just increase. So in the case of logic programs, we will start with the constant 0 assignment, and then we just transform it to slightly greater one, and transform it again to slightly greater one. We are just only setting those variables to 1, to true, which should be absolutely set to 1, and eventually we will just converge to our final solution. And this final solution will be computed by this supremo operator, so that's why we are introducing this guy here. And we want to compute things using the supremo operator, so we should just collect some very basic facts which will be used throughout the whole semester. So for example, what is the supremum of the empty set? So it's of course the least upper bound of the empty set by definition. So the second question is, what is an upper bound? What is an upper bound? of the empty set? Now that's a good question, and for this we can of course expand the definition, so that's what we always do. So an upper bound of, so X is an upper bound of the empty set if and only if for each element of the empty set, of the empty set, we have this element being smaller than or equal to X. Okay. Now, this always means that for any element of the poset, of the wall poset, we have this implication of if it's in the empty set, then it's a lower bound of X. Now, this implication is always true because, of course, this part evaluates the false for any possible element of a set of the universe of the poset P. This part of the statement that Y is a member of the empty set, this is false. And because the left-hand side of the implication is false, the implication itself is true, so it's 1. Which means that for any possible Y, we have a true statement, which means that this holds for any possible X, which means that always. So I can write this like this: bottom is a lower bound of the wall poset, or dually any element of the poset is an upper bound of bottom. And back to our original question, so this means that the least upper bound is the least element of the poset. So the suprema of the empty set is always, by definition, the least element of P, if it exists. The least element of P. And usually the least element of P is denoted by this bottom sign, usually. And that's why in the case of pointed posets we also used this notion, this symbol, because it's quite usual. Then if a poset has a least element, then it's usually denoted by this one. So for example, in the poset 2, 3Z, right? We have bottom, which is just a 0, 0, 0, everything is 0 assignment. So that will be the least assignment, that will be the least element, and that will be denoted also usually by bottom. Yeah. So the supremum of the empty set is always the least element of P, and of course dually, and I'm just listing the things again, so the infimum of the empty set is always the greatest element of P. Yeah. If it exists. So of course it doesn't always exist, but yeah. Now again, I'm just trying to build up some quick facts, and then we will come back to the logic programs and analyze the logic programs with this framework we are just trying to build up. So if another statement is that if for each element of X there is an element Y in some other set Y for each element X of small y, with X being smaller than or equal to Y. So what do I have? I have two sets, X and Y. These are both subsets of the poset. And if in X there is an upper bound of x in y, then any upper bound of y is also an upper bound of x. Yeah, that's also just a statement, so let's just prove this. So what do I have here? So let's say z be an upper bound of y. Which I told you already. I think that we are denoting this by this notation, so y is smaller than or equal to z. This is the same. So z is just a member of the poset, it's just an element, y is a subset of the poset. And now to show, I want to show that x is also a lower bound for z, or z is an upper bound of x. Same. We have to show that that x is smaller than z for each member of x. Yeah, that's the definition of being an upper bound. It's for each x of x. Okay, so let x be a member of this large x. So we know that there exists a y for which x is smaller than or equal to y, and this y is a member of the set y. And so basically we have, from y being smaller than z and the small y being a member of the y, we get that y is smaller than z, and we also have x is smaller than y. Now here where the transitivity property kicks in, so we get that x is smaller than or equal to z. And yeah, that's fine. And that's fine. And that's fine. So basically, if I just have a base set and I just increase some of them, some of the elements, or I'm just increasing or keeping them in place, and I just deduce something as an upper bound of the new set, then this upper bound will be also an upper bound of the original set. Okay. Now, from this, I can deduce, and of course, it means that if x and y are both subsets of the poset subsets, and say for each x there is y, x in x and y in y, with x being smaller than or equal to y, and for each y I can also find an x with the same property, with the same property, then it means that each upper bound of y is also an upper bound of x, and each upper bound of x is also an upper bound of y. Then it means that the upper bounds of these two sets coincides. Then the upper bounds of x and y are the same. Okay, because of the statement in the previous slide. Yeah. So this basically enables us just to change our set a little bit and deduce that if the supremum of a set is computable from that point, then it will be the same, because if the upper bounds of x and y are the same, then it also means that the supremum of x is the supremum of y in that case. Yep. Absolutely. So we will try to compute suprema of sets, and this will be easier if I can change the set state. Like, for example, just one minor application which we will see in detail. So for example, if X is an arbitrary subset of the poset and it has a bottom element, then the supremo of X is the same as the supremum of X plus the bottom element. So if you just include the least element, then you won't change the supremo. That's a statement, and it's a consequence of the statement on the previous slide, because so there are two cases. If X is the empty set, then basically what we have here is a supremo of the empty set, which is the bottom element. We've already seen this. And this guy here is, well, if X is empty, then I'm just inserting the bottom element into it, so it's just the supremum of a singleton set, and the supremum of a singleton set is always the element itself which is in the set. So the supremum of the set containing only the A is always the A, no matter what it is. So it's good. Then if the cardinality of X is small, is at least it's a positive thing, or I would say that if X is not the empty set, or I would say it otherwise, these are the same, then for each member of X there is an upper bound in X in a premise. So for each element in X there is an element of X and the bottom element, with X being smaller than or equal to Y. Of course you can choose Y to be X, so it's just Y. So if you just increase your set, you are just pushing more elements, then this property will hold, so you will still have upper bounds for the original members of the set. Now for the other direction, for each X in X plus bottom, there is an upper bound in the original set, because there are two cases now. So if X is the bottom element, then any element of X is fine, because the bottom element will satisfy this relation if you have anything on the right hand side. So if you choose one element of Y, and this is where it's important that X is not the empty set, so that's what it was treated differently. So in that case any Y element of X is fine, and then if X is not necessarily the bottom element, that it's a member of X, then the Y can be chosen to X because it's also a member of X, and reflexivity comes in, so that's also fine. X is an upper bound of X. Yeah, so it's written here. So from these two statements we get that the upper bounds of these two sets are the same, and in that case it's already proven that the supremum of X is the same as the supremum of X union the bottom operator. So we will use this when we will prove some convergence property, that we just push the zeros, push the bottoms always in each iteration from below, but it won't change anything because adding the bottom symbol won't change the supremum of the set itself. So that's how we will use this fact. And there is also some other statement. So if X is a subset of P and Y is also a subset of P, and X is smaller than or equal to Y. Now what does this mean? This means that for each element of X and for each element of Y we have this relation. So basically this is the same as stating that Y contains not necessarily all, but some upper bounds of X, and X contains lower bounds of Y. Yeah, there's some lower bounds. Then we have several things. So for example, then if I'm just increasing X slightly, so X is smaller than the supremo of X, but it will be still smaller than or equal to Y. And the second statement is that if I'm just decreasing the Y by just choosing the infima of this set, then it will be the second statement, and also they will be in a nice arranged chain, assuming these exist. So if this exists, and if these exist, and if both exist. Yeah, so if these notions exist, the supremo and the infima, then they can be pegged nicely between X and Y. And these are just single elements, X and Y were sets, so sometimes it will be easier just to focus on one single element of the poset instead of a whole set of elements of the set. So that's why we are just, if we are just dealing with two sets, then eventually we will just deal with an infimum and the supremo, and that's why it will be useful. So let's just prove this. Let's start with this, and let's assume that X, the supremo of X exists. So of course X is smaller than the supremo of X, since so it's the supremo of X is the smallest, the least upper bound of X, which means that this is an upper bound of X. So since by the supremo of X is always an upper bound of X. Yeah, that's fine. Now, for that part of the supremo of X being a lower bound for Y, we show that for each possible I, we have the supremo of X being a lower bound of Y. Now that's exactly what's written here. So the supremo of X is just an element. This is a lower bound of the set Y if this is a lower bound of each element of the set, which is written here. So that's the same. So this is exactly the same as being as Y of X, the supremo of X being a lower bound of Y. So that's the same. So if I just prove this, then I'm ready. Now to show that for each element of Y, well, so since Y was a member of Y, small y was a member of Y, this means that Y was an upper bound of X. So this means that because of X being smaller than or equal to Y, this means that Y, this small y, is an upper bound of X. So Y is an upper bound of X, and this guy here, this is the smallest upper bound, the least upper bound. So on one side, on the left hand side, I have the least upper bound. On the right hand side, I have one upper bound, which means that the least is always at most any of those guys. So this is fine. So this is the least upper bound. This is just one upper bound. So this is proven. And this means that this is also proven, while this was sort of trivial. So we have that if we have two sets and y contains upper bounds of the members of X, and the supremo of X exists, then the supremo is still a lower bound for Y. So you can increase X a bit, but you will still be below Y, below or equal to Y. Now this is sort of similar. So this is the same thing by duality, but you are just playing with lower bounds and the largest amongst them, the greatest amongst them, instead of upper bounds and the least amongst them. So it's the same. Now for this chain, for this particular chain, I'm just trying to, okay, so I have X is smaller than Y. Then if I just apply the first statement for these two guys, then X will be smaller than or equal to the supremo of X, and it will be still smaller than Y. Now that's fine. And now I will apply the second statement, but to these two sets. Okay, so this is just the one element, but it's the same as having a one element set. And from this, if I apply the second one, which says that if I have two sets X and Y, then for the larger I can take the infimum and it will fall between these two guys, which is exactly what I need. So from this, if I just continue, then I will get that the supremo of Y will be between, so the infimum of Y will be between these two sets, and of course this guy is preserved. So that's fine. This just basically says that if I have two sets, one of them being above the other one, then I can take the supremo of the smaller guy and the infimum of the higher guy, and the infimum of the higher guy will still have the high ground. So that's a quite useful statement. And I think I only have one last statement just before we are going back to the setting of logic programs, and we will need these math concepts for studying the canonical semantics of logic programs. And the last statement is just that the suprema can be swapped if they are next to each other. So if I and J are index sets, index set is just it's just the intention. So what am I trying to do with my set? It means just I will use the element for indexing, but they won't be ordered in any particular way. So if I and J are index sets, and for each I, in I, and J, in J, we have some xij, so it just means double indexing. Then the statement is that the supremum of I in I, and inside this we have an inner supremum over J in J, xij is the same as the supremum over J and the supremum of I. So it just says that if I have two supreme operators next to each other, then I can just swap them, assuming that the indexing of the innermost guy doesn't rely on the indexing of the outermost guy. So it just means that it can be swapped if they are just standing next to each other. And in fact, this is the same as taking the supremum of all the xij's, I in I, J in J. Now I'll only show this, that this guy is the same, because it basically says that it can be flattened So if I have two supreme operator next to each other, then that's some sort of nested loop, and it can be made into one single loop, basically says. And of course, if you already have this, then the order of the element won't matter. So if I'm just showing this in red, then it's also the same for this guy, because the flattening of these two suprema yields the very same set. Well, apart from the fact that it's indexed the other way around, but there is an isomorphism between the double indexed part, so it will be the same. But what does it mean? I'm trying to depict you. So we'll have I'm just drawing something which slightly resembles as a matrix. Yeah, x1 3, x1 4, and so on. And then I have the second row, 2 2 2 2 3 2 4, and so on. And I also have 3 1 3 2 3 3, and so on. Now basically what the statement says is that if I'm just taking the suprema of the first elements, so I'm just taking the suprema of the first row, so that will be the suprema of the xi1j, j indexing the columns. And then for the second, I'm just taking the suprema of the second row, and it will be the suprema of the x2j's, j and j, blah blah blah. And I'm doing this for each row. Now there can be an infinite number of rows. There can be a quite large number of infinite rows. So some ith in the ith row we have the ij, j and j, but I is fixed. And then I get several elements, and then I'll just take the suprema of these guys, and that will be the suprema of the j's of the i's of the suprema of the j's of the xij's. So there's just take the suprema of the rows, okay, you will get these supremas, and then take the suprema of the results, and that's the double stuff. While the other thing is basically just taking the suprema of all these guys in one single step. And it says that it's the same. So the statement is this: you can just rearrange. You can rearrange taking suprema, and you won't lose anything, assuming the supremas exist. So it's yeah. So it's if the expression has a meaning, so if all the suprema in the formula actually exist, then the result is the same. This is what it says. And to prove this, we are just showing two things. The first one is that the suprema of the xij's, if we just index them into one single set and then take the suprema of this in one part, that's at most the suprema of the i's, and the suprema of the j's, which I will just write like this: xij, j and j. This is the same as stating the suprema of j and j xij's, so it's just moving the loop index into the set from the counter just below the supreme operator. So for this, I will just it's enough to show because of the definition of being a suprema. So this guy is this in the left hand side is the least upper bound. Of the Brown set, so it's of xij, I and I, j and j. Since on the left hand side I have the least upper bound, it's enough to show that here on the right hand side there is an upper bound. And of course, if this guy is an upper bound now, so basically for each x, so I can just say that it's enough. It's enough to show that for a fixed I and j, we have xij being a lower bound of this. I'm just using a different letter for indexing, it doesn't matter. And the supremum again of the xi prime, j prime, I prime in I and j prime in j. And just introduce a new variable because yeah, so it's so on the left hand side it's a constant anymore. It's just not a running index anymore. And so, but here xij is a member of a set, of such a set, right? So of course xij is a member of the xi and j is running. Oops, this is redundant here. So xi is fixed, j is running, and j prime is here. Of course, because here j is running through all the set j, so it contains the xij as well, which means that the supremo of this set is at least as large as xij, because the supremum of a set is always an upper bound for all the elements of the set, so that's fine. So xij is smaller than or equal to one of these elements. And again, let's just use the term xi star for the supremum of the set. So of the xi j prime in j. Okay. So this just says that xij is smaller than or equal to xi star, and we have the set x y prime star I prime in I, and the supreme of this that's on the right hand side is the same, and xij is smaller than or equal to xi star, and xi star is a member of this set, and this guy here is the supremum of this set. It means that xij is still smaller than or equal to the right hand side, which means that I eventually shown that this guy is at most as large as the other one. So basically, if you just take all the elements supremo at once, then it's at most as large as the row-wise supremum's supreme. But that's only one direction. We still have another direction, which is the second, of course. So the second direction says that the supremum of I and I and the supremum of xij prime, it can be, so since we don't have any more running indexes at this point, it can be j in g. I is already fixed at point at this point. So this is smaller than or equal to the large, the flattened supremum, so it's just the supremum of all the x and j's I in I, j in j. Okay. Now for this, again, I have, and remember it was denoted so this I already used the notation xi prime to denote this expression. So is just the supremum of the xi primes I in I. This is just the same of these two statements are the same. So the supremum of a set is a lower bound of something. Again, the is of a supremum of something. So what should I do? All right, now I have that for these sets. So for a particular set x, I, j, j in j is of course a subset of the whole set x, I, j, I in I, j in j. And if the left-hand side is a subset of the right-hand side, then for each element of the left-hand side, I have an element on the right-hand side, which is an upper bound of this. So which means that any upper bound of this guy is also an upper bound of that guy. So the supremum of this guy here is also an upper bound of the set and the right-hand side, which means that it's an upper bound for this set itself, so it's just becoming smaller than or equal to. So yeah, this set is smaller than or equal to the supremum of that guy, because that guy is still an So since any upper bound of the right hand side is an upper bound of the left hand side, this means that their supremum is always still an upper bound of the left hand side. And now we can use the fact that if I have a set and another set, then I can take the supremum of this set and it will fall between the two notions. So it just says that if I'm applying the first amongst the three cases, xij, j in j, is smaller, is a lower bound for its own supremum, of course, which is a lower bound of this original set. Yeah. And this holds for each I. For each fixed I, we have that the row-wise suprema are each being smaller than or equal to those guys. So this is just for each I, we have that xij is smaller than or equal to xi star is smaller than or equal to this guy, because yeah, xi star was the notion for this innermost part. And then I have that I have a bunch of elements xi star and one single element, this guy there, and this guy, the rightmost guy, is an upper bound of each of these guys, which means that the supremum is the smallest, the least upper bound of those guys, is still smaller than the right hand side. So what I get is the supremum of this xi star is actually smaller than or equal to this part, which is just the same as I wanted to prove. So basically what we just achieved is that if the expression has some meaning, then you can swap the neighboring operators of taking the suprema. So that's the primary reason why we had this proof method. So you can just swap these guys. And also there were some other statements, this being the most powerful one amongst those small stuffs. And yeah, that's also important, that you can just plug in the least element and nothing ever changes. Okay, so right now we have quite a bunch of well, I can call it of supreme juggling rules, and we will apply them to the context of the logic programming part in the next video in the next week. Till then, bye bye.